Yeah, exactly. That's literally what I'm doing. I'm just changing the constant. Yeah. Well, yep. Exactly. Yeah. It was like the little pages. Yeah.
Okay, back to the class. Our last lecture. Hey guys, let's concentrate on the lecture for a second. When is the exam? I don't remember. Do you know the date? 29th?
On the website.
That's probably the date. Okay. So we'll discuss next week the format of the exam, but roughly everything should be covered. But let's finish this. Let's finish the file systems, our last real lecture. And it's kind of fun because, again, while the file systems will look maybe slightly different in the future, many ideas will be there still. Okay, so last time we kind of looked at what will be inside the file system, and we said, okay, there will be this collection of those layers starting from like, I was explaining them bottom up, but really it starts from the system calls. A system call will use a name_i function, which resolves like a path, right? So like slash foo bar into something, into an inode, right? So this path name level will perform this lookup. And also there will be a directory layer level, which essentially allows you to add multiple files to a single directory. Then from directories, you go to files and inodes. And from files and inodes, you go to something what is called a logging layer or journaling in modern file systems, which ensures atomicity of your writes. So either everything happens or nothing. And then a buffer cache, which ensures synchronization and performance. So let's quickly go through a typical layout of a file system and just take a look at each of these layers in some level of details. So if you have a disk, so a typical file system will look like that. So it will have something, what we've seen before, right? Remember the boot sector. So really remember the bootloader, which we started booting from. Right? This sits here. Each of these blocks is only 512 bytes. So and remember the BIOS, the convention on the PC platforms is that the BIOS will try to fetch the boot sector from the boot code from sector 0. We'll load it in memory. Does anyone remember the address? 7C00. So I remember it for at least a semester, then I forget again. But 2 zeros. It's a lower address just because it might you start in real mode, right? And it jumps there, and this tiny boot code boots the rest of the system. And on modern machines, you've seen like if you really ever looked into the BIOS or like into the boot screen, you can say, okay, can I want to boot from the network, for example, or I want to boot from a USB stick. Well, BIOSes are powerful. So BIOSes are like tiny operating systems on their own, right? So, and they can do it, right? So they say, look, instead of like implementing this legacy convention of fetching this boot sector, I will just go and fetch something from the network, right? And the BIOS, which sits in the firmware, which is the read-only memory on your motherboard, will just have enough smarts to do that, right? But in our class, this is what's done. There was a question?
Yeah, this is the physical location on your disk, no like layer virtualization.
Right. So those numbers 0, 1, 2 are real, just you can say physical numbers. So if you have a spinning disk, that will be like allocation on an okay, that's a good question. So modern flash devices, right? So I don't know if you guys like looked into them. So, but NVMe attached disk, right? So it does implement a layer of virtualization inside because of the limitation of how the flash is implemented and the fact that you can only write a chunk of data at a time. And also they try to balance what is called aware, meaning that if you write multiple times, it stops writing at some point or produces an error. So they try to implement a layer of virtualization over the physical space. And so really, there will be a tiny CPU running on this card, like, let's say depends on these days, it can be quite powerful because you can actually run your code there in some systems, right? And so roughly speaking, that will implement something what is called flash translation layer, FTL. For spinning disks, there will be a similar deal, but much simpler. So if you really have a spinning drive, there also will be a microcontroller, but it will mostly be implementing some kind of a caching layer. So those disks are also smart, and they say, okay, we have some memory capacity. We're gonna cache frequently read and written blocks and stuff like that. But I don't think they virtualize the space, right? But effectively, let's say if you set address 0, then this thing resolves maybe at some location on a spinning plate or maybe in your flash banks. And to you, it looks like physical, although internally there might be some virtualization, but probably it's below the level of our class. Good. Okay, cool. So boot sector is there, so mostly used for the operating systems to boot, right? But the file system really starts in sector 1. So, and this is where the operating system knows that the file system will have something very useful in this sector 1, which is called a super block, right? And effectively, the super block kind of encodes locations of this other areas, right? By mentioning their size, right? So, and then the file system, when it bootstraps, it says, okay, I know that I have a logging area of some number of blocks, inode area of some number of blocks, a bitmap allocator, which keeps track of the availability of those blocks in the data area. So essentially just says free or taken in the data area where you really will be writing your files, right? That's encoded in the super block. Questions? Kind of, yeah. Wow, yeah. There is a similarity to an ELF header, yeah. But it's not surprising. So you need to start from something and then unfold dependencies.
Will you be discussing this partitions?
No. Very simple. We have 90 minutes minus 10. There will be no disk. Yeah. Just that I don't know much about disk partitions either. So very simple. This is how x86 does it, and it represents kind of the gist of what modern file systems are doing as well. Okay, so the first layer, the first area is this journaling area. We're going to talk about it, but at a high level, it's like a temporary buffer in which file system will be writing writes and accumulating them here, and then later installing them in a data area. So you will see later that when you do a write, the write doesn't go directly into the data area, but instead just first goes into the logging area and then is moved into the data area. And this is to ensure transactional semantics. So either all writes happened or none of them happened, right? And that ensures consistency of the file system. So we'll talk a lot about it today. The next area is inodes. So, I mean, first of all, this area is really just an array. And each element of this array is a number, starting from 0, 1 to 3, right? And this gives you an inode number. So you've heard of it. You say the file is really an inode, and inode has a number. So, and this number is an index in this array, right? And what are those inodes themselves, right? So if you think about it, so when you have a file, so logically, a file starts from 0, right? And as you write it, it just kind of grows like an address space, right, to some size, right? But physically on disk, it can be kind of like a virtual to a physical memory mapping. It can be anywhere. So because you're allocating those blocks, and often sequential blocks are not available, so you're just allocating them somewhere in some areas on disk, right? And so inodes effectively remember they look kind of like a page table, which remembers if you say, look, I want to read block 0, you do the translation and it points to some physical data block on disk, right? So very similar to a page table, very similar organization, also a radix tree, but with a twist a little bit, right? And effectively, the inode looks like this. So this is your kind of the page table-ish data structure. And effectively, when you say, look, where is my block number 55 located? It just goes here, reads this table, figures out that 55 is should be like in this table, and then it will get a pointer to the data area, right? So it's kind of like each file has this tiny translation table, which translates, keeps track of where the files are physically on disk, and we will talk about it more about them, but just to have this idea, right? Any questions about it for now? Good. Yeah.
Is the inode area variable inside of it, or is it always?
Well,
Because we want
correct. So in a real full feature file system, it probably can vary, right? And not probably for real. In x86, it's defined at compile time. So when you compile the kernel, you will, well, again, so everything is encoded in a super block, right? So, and the x86 has a tiny tool, which kind of like if you ever formatted a new disk, so it formats a file system for x86, right? And it says, it takes an input and says, okay, like create me a file system with that many inodes and with that many data blocks, right? And then this data is effectively written in a super block. The kernel itself, I don't think there's any static knowledge about the inode area size. So when the x86 boots and opens the file system, it reads this super block from disk, looks at the size of the inode area, logging area, and just goes forward from there. Maybe, if I understand correctly, maybe it encodes the size of the journaling area, because some journaling code, this logging code, it needs to keep track of how many transactions are in flight. Because if you say, I can take another one, but then you run out of space in a logging area, then everything fails. So maybe there is this limitation in the code of the file of the x86. Maybe it's not dynamic, but maybe it is. Don't remember exactly. Okay, so inodes are there, right? So, and like we're gonna talk about them. Then the bitmap area is literally just an allocator. So each bit of this area, which is not super large, keeps track of whether a specific block on disk is available or not, right? So it's very similar to a memory allocator. And you can imagine, okay, but that surely will suck, because if you start scanning those like for free blocks, if your file system is getting full, your scans will be longer and longer. And eventually, like every write to a file system will be slower and slower, right? So really, a good allocator should not look like this. And I agree with you. So like a good allocator will be something like a linked list of those blocks. But in x86, just again, for simplicity, it's a bitmap, right? And so allocation is done with a linear scan, right? The longer the scan, the slower everything gets, right? But it keeps track of available blocks in the data area, and the data area is really where the data is contained, right? So when you like remember you do a file write, for example, right? So somewhere inside the kernel there will be an inode. This inode will like match this entry in a file system in the inode array. So let's say inode number 55. The operating system will read this information, will read this entry, will read additional page table entries from the data block, and then eventually when you write like into location, let's say 105 on disk, this will translate to a specific data block. And if you write something like hello here, hello will be written here.
What's 105 here?
105, just a random
example of the content, right?
Yeah, it's actually hidden from you, so you probably right. I shouldn't say 105 here. I was saying that you're writing a block 105, but while you're writing, what you really do is just you simply writing data. Internally, there is yet another layer here, which says which is called a file. And this layer keeps of a current position in a logical space of a file. So when you you open a new file, the position is 0. You write 10 bytes, this offset within the file is 10. And then it keeps growing. And you can reset the offset, right? Remember, with a seek system call, right? And so, but really the hello goes here, right? Again, question. Can you restart? Sorry, I get distorted for a second. So
the inodes are sort of pointing, they like have a data structure, like a table that eventually points to the data, like where the file's sitting.
yeah.
If there's multiple blocks, how do you encode that so that you can find other blocks of the same file?
Yeah, so I will show the encoding later today. At a high level, I mean, multiple encodings are possible, right? And multiple encodings were used in different file systems. x86, the encoding in x86 is the following. Let me quickly explain it, but we can come back to it later. So this is the actual inode entry in the inode array. To make a quick optimization to support small files, the first 12 blocks are kept in place here, right? And if you say, look, if my file has more than 12 blocks, which means 12 by the file is larger than 12 multiplied by 512, right? Then it has a pointer to a data block, which contains the whole block of entries again on disk. So this will be kept in a data area. And each entry, if the one block is 512, each entry is 4 bytes, you have a total of 128, right? So your max file size is actually 12 plus 128 multiplied by 512, right? Not a huge size, but it's just an x86. And you can imagine that, well, like if I want bigger size, yeah, we can add one more level of direction, right? But this is the encoding. So essentially, like there will be logic which translates the address, like an offset within a file. It checks whether it falls into this first 12 entries. If yes, you immediately go to the data block. If not, you read the indirect block. And then after that, you read the data block.
In a real operating system, they like usually it seems like so like do they try to when they try to set how many like addresses and indirections put into the encoding, do they try to like set that equal to like a normal like full disk so that the size could be of one file and basically your entire hard drive?
Again, I never was working in file systems as core area, right? The encodings which I've seen, first of all, even if I ask you a question on the exam, you should answer. Say, come up with encoding which supports size of infinite, files of infinite size. Okay, let's do it quickly now. So what's the encoding? How can we keep track of how can we implement files of infinite sizes?
The last entry in the indirect block, the indirect.
Correct. So what you're saying is let me quickly, just wanted to like, for example, here. So you say, look, if this is my inode, this is the 12 entries, right? Direct entries. This one points to an indirect area. Indirect. And you say the first 127 will be pointer to the data blocks, right? But the last one will be a pointer to the next indirect area, right? It's kind of like a linked list at this point, right? And those will be pointers to the data areas. And again, the next one potentially can go to the next indirect area, right? Like that's very simple, implements a file of an infinite size. I think this layout was actually implemented in a FAT file system, which was used by Windows for a while, Windows 80, 90, whatever, like Windows 3, Windows, what is it, 95, 98, whatever it is. Then they switched to NTFS. So the reason to switch, so what is The good thing about it is that really it does support files of indirect size or of infinite size. What's the disadvantage?
Size.
Well, no, it's good. That's what you want. Imagine you're like in the movie industry, right? And maybe they did have, but this conceptually, this scheme doesn't have it, right? But they maybe have it, yeah. So, but what is wrong with this encoding?
Like you typically try to write the end of the lab.
Yeah.
Just get
Correct, because you have to traverse the list, right? And it becomes O(n) operation, slow, right? So not ideal, right? So fat died, right? Didn't become very popular. But you can imagine a slightly more efficient encoding in which those layers, like you represent everything as a tree, and then you have to think about how this tree can grow essentially to an infinite size. Again, if you're taking an algorithm class, I'm pretty sure that people will teach you how to do it. But it's not super hard to do a simple thing. It's hard to do the one which is efficient. Again, someone mentioned Prashant. I forgot the last name. What's the last name? Prashant Pandey. So he actually worked on a file system. He joined University of Utah, professor here right now, from VMware Research, and they worked on a file system which was designed to support super large files. There's like a lot of magic there because really to optimize the number of disk accesses, right? So they try to keep this metadata about the file in memory. And then I think they used some abstraction, which is called B plus epsilon tree. So again, there were like trees, there were B plus trees, and there's B plus epsilon trees. It's interesting. So yeah, so people do optimize those things too. Just like it's a very clever algorithm for how to push data to disk and keep something like, and even how many layers down on the disk you have to go, like meaning that you traverse smaller number of layers.
five is forced to remain in memory, or is it hard for specific indirect blocks broken?
Right. Typically, in x86 at least, and in most typical file systems, they are lazily brought in memory when needed. You can imagine some funky use cases. And again, I mean, I apologize for those anecdotes, but I had a friend who was doing like a big startup on data storage. And so one of the things which they were doing is that storage for the data center. So like organizations which run a lot of virtual machines. So they were pre-computing. It was before we had good AI, but they were pre-computing and predicting the working set of a file system. And essentially, when people coming back to work at 9 a.m. in the morning, they were pre-caching the working set, typical working set, so they can start those virtual machines for everyone. So again, kind of a natural idea how to build it is a magic, right? But so you can do those tricks. You can pre-cache. I've seen even like modern file systems, I think, try to guess and do the prefetch of those blocks ahead of time. You know, like varying from very simple prefetches, like prefetch the next block, to developing a prefetching algorithm which tries to predict which blocks will be read next and bring them in memory, right? So to what degree Linux does it today, I'm not an expert. You can read also like a lot of literature on file systems, which that's their main research to these things.
Isn't it also to have infinitely large, because depending on the metadata, you could have a file that takes up your.
Correct. So what you're saying is that what if one user who wants to bring everyone down to just like exhaust the space in the file system by writing zeros? Correct. So typically you will address it with some kind of a quota, and like then it becomes a policy problem. Who has the larger quota? What is a meaningful size, right? But again, it's one level up. You can implement those policies outside of the file system, right? But if the file system supports infinite files, maybe it's not bad, right? In many cases, right? But again, you can we can talk more, but probably should get going. But you can design different layouts of those inodes to make sure that you support different use cases, like small files, where you have a ton of very small files, maybe like a web server, because typically you're serving small, wow, these days it's different, right? But maybe like a stream on a Facebook or something, on a Facebook page. And occasionally you stream movies, right? And then it's a different setup to support large files. So stuff like that. Okay, just to warm up, let's do a quick poll here. Very simple question, only people who are sleeping cannot answer it. What is inside this bitmap area? And let me quickly switch here, start the poll. It's live now. Oh, wow, it's pretty wild here. People have good guesses. Close this. So we have two groups of people. Some people believe that the bitmap keeps track of unused file in a file system. Is that true? No one is asleep? Good. Majority of people in clouds believe that bitmap keeps track of unused blocks in the data area, and that's correct, right? So that's a simple allocator. Okay, everyone answered? Have to get going. Okay, good. I will receive a lot of requests to reopen the poll because we're still voting. Okay, let's vote for 2 more seconds. Now everyone, this is the delay, so we can measure the delay to the live stream, right? So, okay, let me go back here. Let's close the poll. Can I close it? No, I cannot close it. Why? Okay, let's switch back to the lecture. Okay, quick detour. Okay, got it. So let's first at the very, like, we spend a lot of time today, or majority of our time, looking at the buffer cache and the logging layer, right? So those are the most involved layers, and then the other ones we just kind of cover at a high level. But it's okay. So the buffer cache sits at the very bottom of a file system stack, right? So it's essentially provides those two functions. One is synchronization to make sure that only one process reads a block at a time, right? And it's like, we'll see how it's done. And caching essentially just has a memory area in which it will be temporarily caching the frequently accessed blocks, right? And will maintain the history of which block was cached recently and then evict the oldest blocks from the cache, right? So again, so if I ask you a question, so how would you build this if you were a designer of a file system? What will be this data structure?
Right.
What? A set? A set is a good data structure. So since we are operating system designers, code everything in C, how do we build a set? I know that it's lovely at the level of
I know, it's really
a hash table. Well, a hash table is a meaningful data structure, right? So we can probably a what? A tree. So okay, hold on. Let's talk about the hash table. So hash table is fine because you can bring blocks from like, imagine you have an area where you're gonna be caching data temporarily. You can bring a block from a disk in memory, right? And the block number will serve as a key, and the data will serve as value, right? For example, and so that's nice. So it will quickly allow you to quickly check whether the block is already cached, right? So this is a good. However, how will you build this eviction functionality? Meaning that you keep tracking which blocks are sitting here for a while and were not used for a while as well. So maybe we should kick them out to free some space in memory. So how is that done? How can we do it?
whatever metadata is in the value portion of the hash table also kind of forms the linked list of something or using.
Correct. So you say, look, did everyone get it? So you say, instead of just keeping the data from disk as a value, we also will keep a couple of pointers here, which connect the elements of the hash table in a least recently used order, right? And then you know that the element at the very end of the list is probably was not used recently, and you can kick it out, right? Free some space in this hash table proactively, right? So, and x86 does something similar. Instead of a hash table, again, for simplicity, they use just an array, and they just maintain a linked list, meaning that if you use an array instead of a hash table, you really have to, if you want to find whether the block is inside this, is already cached, you have to scan the entire array, which is not fun, but that's what they do. But a better algorithm would somehow resolve the block in a hash table style. Or maybe, as you said, you can use a tree. Same tricks, a kind of maybe a sorted tree, and then again with a linked list connecting the elements to maintain the list recently used elements, right? But the tree will provide you with log n search time, right? So here it's ON, right? So the buffer cache in x86 is implemented in a very simple manner. So you say, look, this is literally my buffer cache. I have an array of n buffers, right? And each buffer is the data block, as we said. So this is the value, and the elements of the graph and next pointers in the list, right? So it's very similar idea which we just suggested, but instead of a hash table, they just simply use this array, right? For simplicity, okay? So let's see how it works. So conceptually, again, a couple of interesting fields. So this is really where the data is cached. So it's 512 bytes. It can be in different states, and we encode it in this flags field. So it can be valid, meaning that we already read data from disk and no one wrote it, or if it was overwritten, it will be in a state of dirty, meaning that before throwing away this element from the cache, we actually have to write it back to disk. Otherwise, we're going to lose the data. And busy means that it's locked and someone is using this block right now and you have to wait, right? So kind of synchronization discipline. So just again, if you have multiple disks in a single buffer cache, you say, look, and this pointer is a pointer to the actual disk device, right? Encoded as a number, because you might imagine a system with multiple physical disks, right? And that's actually the block number, which we are caching. And the linked list is maintained. So starting from this head, and then you can look at the previous and next elements, right? So a typical workflow is the following. So you have the following functions. So you have a function which does the block read, and it also acquires the lock. So essentially, when you do a read, you own the buffer for a second in a buffer cache. And you can do a block write, meaning that it will write the block back to disk. However, you have to do a block release after that, right? Otherwise, no one else will be using it. No one else will be able to use it, right? So a typical flow will be read the block, which tries to look it up in a buffer cache. So if the block is already there, you get the pointer to this block, right? If the block is not there, you figure out an empty position, like essentially this is where you're going to do a scan instead of a hash table lookup. Figure out the empty element in the buffer cache, read it from disk through a block disk driver, fill in the data, and then return the pointer to this location, right? At some point you say, look, maybe I changed the data here. You do the write. This write flushes the data back to disk. However, you still own the block, and then you do the block release, which means that at this point, the buffer cache can evict this element from the cache if it reaches the very end of the least recently used list. You're right. Let's double check how it's done. Actually, maybe I'm wrong, and the right. You probably leave it in a buffer cache. So let's scroll through the slides and verify this. Any other questions? Most likely it can hang out there for a while, right? Okay, so this is an example. So this is part of the journaling or logging code, which essentially just installs, like, commits a transaction. So this is what they do here. So they read two blocks with the bread function. They acquire pointers to them, right? They copy the data, like literally modifying the data area in the block in memory, and then they write one of the blocks and release both of them, because only one of them gets written back to disk, right? But just to get to the next level of details, let's take a look at how this buffer cache works. So the block read function essentially says, okay, it tries to locate the block in a buffer cache with this beget function, right? So beget itself, as I was saying, so we'll scan the linked list, and what it does here is that it says, okay, I will go from the beginning to the end of this block array, and it says, okay, look, if the block has the matching disk and a block number values, then that's my block. That's what I want. It, however, can be in a busy state, right? So, and if it is in a busy state, I will go to sleep. And we discussed sleep last time. So instead of like spinning, you really like yield the CPU to something else. However, if it's not busy, I will set the flag to busy. And by the way, you're already operating under this bcache lock already. So everyone else who wants to do a beget will be spinning on this spin lock, right? And you release the buffer cache lock. At this point, you essentially return it to the user, right? If you, however, went to sleep, when you get out, you will have to essentially like redo this scan, because who knows, maybe you lost the game of acquiring the locks and stuff like that. And this block is gone from the cache. So you have to really redo everything. Again, low level detail, maybe it's not that important, but anyway, so let's imagine this is the flow. If you say, however, okay, we didn't find the block, right? So what we're gonna be doing here is that we need to figure out a block, an empty block in a buffer cache. So again, not the most optimal optimization, but you keep scanning through the elements of the buffer cache, trying to figure out a block which is not busy and not dirty. And at this point, you say, look, I found it. It's an empty block. No one is using it. So I will assign my values, device, and block number. We'll set it to busy and return a pointer to this B, right? And however, remember when you started this function, this beget, if your block doesn't have a valid flag, meaning that it wasn't really read from disk, so it was just a fresh empty block, you go to the disk and read it here, right? And this will set the valid flag, and then you return it to the user. So it's kind of like the buffer cache is transparent to the upper layers, because if it was there, it will just immediately return. If not, you have to go to disk and read it, right? Okay, so that makes sense. So let's take a look at what block write is doing here. So it actually, in x86, it actually goes to disk every time, right? And it sets the flag to dirty just to capture the fact that the write is in transit right now, which is, again, you can imagine, is not the most optimal optimization. But that's why when you asked the question, I said, okay, I don't really remember. Why? Because myself, I changed this block buffer cache to actually leave the dirty blocks in the cache and then flush them when I'm trying to find the new available, like new empty element, right? So I will be evicting the dirty ones. But x86 doesn't do that, right? And who knows why? So maybe simplicity, maybe not, but they also always write to disk. It's just when the write is in flight, the dirty is set. That's the logic here. Okay. So we got this, and one in last function, block release, right? So again, we say at this point, we adjust the position of the block in the linked list So we essentially say, okay, we just recently used this block, so let's promote it to the beginning of the head of the list, make sure that it will not be evicted anytime soon. And the idea here is that the logic is that you're going to be using this block again in the near future, so this temporal locality, right? And after that, you say, look, it's actually released, so it's no longer busy, and anyone else can use the same block, but it's cached. It remains cached in a buffer cache, right? So it's not evicted, nothing like that, right? So, okay, at a high level, very simple, right? There are many like shortcomings which x86 is taking, right? So who can name a couple? What is not a good, a couple of not ideal design choices? Let's take a look somewhere here, for example. Who can name a few? If I were asking you, okay, a good job interview question, someone shows you this source code of a buffer cache and then asks you a question, can you optimize it? Correct, right? So this like redoing the work by rescanning the array. So probably that's one of the biggest issues, is that you always have to scan the entire array, right? Mm-hmm. So not a good idea, right? So yeah, right. So that's one. What else? So we can optimize it by replacing the data structure from the array to so here I wanted to ask a question like in what order they're going here. So they are following they're traversing the linked list. So it's really not like an array in the order of the array, but in an order of the linked list, right? So which means that there is some kind of internal dynamics which promotes the most frequently used blocks towards the head of this list, right? Which means that, again, take an algorithm class and they will compute this amortization function or whatever it is to figure out what the real complexity is. I cannot do it myself at this point, I guess. But you got the point that it's not like you blindly scanning. So you bring in the blocks to the front. So looking up the block is probably has a probability of higher probability of hitting it faster, right? At least for the frequently used blocks. But you have to, like, if you're really looking for a free block, then the game might be different. Like, not ideal.
The block won't change position.
The block what?
The block wouldn't change its address. Or like
in the list.
In line 47.
Uh-huh. Yeah.
And if it's busy,
yeah, but it can change a position, I believe, because
but its
address in the array. Well, it might be evicted, I think, as well. So there's a range of good questions what can happen with the buffer cache. So it's a good design exercise, because when you're sleeping, you get woken up, but you might lose the game with some other process which actually releases the block. It get evicted, I think, at this point. So there's no guarantee of what's going on. Another, like what I meant to say is another limitation of this buffer cache is that it operates under one global lock, which means that concurrency goes to 0 at this point. So like if you have a lot of file system requests in your system, everything will get synchronized on this lock and nothing will move forward, right? So only one process makes progress, right? Everyone else just waits. So that's not okay. And so design of a concurrent buffer cache suddenly becomes a challenge, right? Okay, but again, so we have the buffer cache. Let's move to the next layer, which is a logging layer. Let me quickly explain the motivation behind it. So let me go back to this figure, which represents the file system on disk. So for example, this one. Like imagine you're doing a file write, something like a write, right? And blindly, you just simply say, look, I'm going to write, I have a file descriptor, I have a buffer of some size, and I'm just blindly writing. So what can go wrong, right? Because in theory, you say, I'm going to just write one block, right? However, there is like a couple of things which can go wrong here. First of all, you're right, this buffer might cover multiple data blocks, right? Maybe it's on the edge, maybe it's just large, right? Which means that if you say like, maybe you're writing, instead of like 512 bytes, you're writing something like 496 bytes. And it means that you will, like you have a bunch of data blocks written, right? Every time you write a data block, obviously you need to allocate a data block. So you need to make sure that you mark those blocks as taken in a bitmap, right? So it's not just writing the data in those data blocks and they are not consecutive, they're somewhere. And which means that if they're not consecutive, your inode, which sits here, either has to like need an update to those direct fields, or if it has a pointer to an indirect area, needs also an update to this indirect area, right? So that's a ton of updates, right? So you're just writing them, right? And which leads us to the following idea. Okay, what happens if you did half of those writes and then crash? Meaning like lost power physically, or like machine rebooted for whatever reason. Maybe the kernel panicked because other process was doing something and the kernel had a bug, right? So you have half of those writes on disk. So some of these were marked as taken, maybe, but some updates didn't go through yet. So then what happens next after you reboot?
You have unfinished data.
Well, it's typically called inconsistent data. So meaning that the inode, for example, might miss, it's say the file size is larger than first 12 direct block, but this pointer wasn't written, so it's null. So when you try to read this file back, there is no pointer here. And then at this point, you're going to panic again because you say, look, I know that the file has to have like more than 12 blocks, but there is no pointer to an indirect area in the inode, right? Does it make sense? And I mean, I just made up an example of one inconsistency, but there is like a myriad of those possible cases which can go wrong, right? Which you will not be able to even like use this file system ever again, unless you do some very funky cleanup on it and check maybe all the possible like inodes and checks their consistency with a tool which on Windows, I think, on Linux is called FSCK, file system checker, right? And you've probably seen it, right? So, I mean, I saw it a lot because in the era of spinning disks, you lose power. Wow, next time FSCK. Yeah, now it's less frequent, so but still happens. But it's like it's a very bad omen. So meaning that if you see FSCK running, so either you will not be able to use your file system soon. The answer, that's the prediction. There was a question.
Did we not write like blocks?
Great observation. So what you're really saying is that can we somehow come up with some ordering of writes? Like if we have dependencies between them, right? And you say, look, I will first write these, for example, somewhere in the data area, then maybe in the block allocator, and this is my last write, which essentially, if this write goes through, then everything is consistent, right? It's possible. And this approach is taken by, for example, a file system in the BSD family of operating system. It's called soft updates. Soft updates. What do you think is a problem with this?
It's hard to maintain the growth.
Correct. It's very hard. There was a guy, I think it was a guy, who came up with the soft updates, and he built a file system. He wrote a paper about it, but then like it's very hard to maintain. It's very hard to convince yourself, and moreover, like make a formal argument that the order of those writes is correct. It's very easy to make a mistake, and then your file system goes to a toss. But it exists, and I will tell you more. So I think those techniques of soft updates will be coming back. Why? Because when the file systems were the main medium of storing data, the technique which I will explain today, which it will be called journaling, was acceptable. But imagine now, instead of a file system, you have a real like remote memory. So it's DRAM, maybe it's non-volatile memory. It sits somewhere in a data center connected through a network. And it's still like a million times faster than a file system, still a little slower. And then you say, look, I'm gonna use this memory as my persistent storage. And then journaling becomes in your way, and you will try to come up with those techniques of soft updates to optimize this. And people, they went a long way for figuring out how to formally reason and design and simplify the kind of the mechanics of developing those systems which support the soft update style like development, right? But it's hard, right? But people, you will see, like maybe in your professional life you might end up doing something. Okay, so imagine we said, okay, no soft updates, too hard, and that's like kind of status de facto state of file systems today. So what else can we do? Like, how can we avoid this problem? Like, make sure that those writes are either all of them hit the file system or none. So what can be the trick? Anyone took a database class? Transactions, okay. How do we do transactions? Kind of, but can someone explain it better? That probably like you trying to explain the, what is it, asset consistency, or what is it called? But no, like let's just take it a little bit simpler. Just simple problem of not losing the rights. How can we do it?
You just put the data in the node, so it's there, and then once it's there, you start figuring out the name and then once that's done, you go through the node. So if a crash happens in the middle of the
Okay. No, agree. Like clearly you took a similar class before, so you know the deal. Let me explain it for everyone. Okay, instead of doing those like 10 different writes, which go here, maybe to the inode area and maybe to some data area, let's say we have 1, 2, 3, 4, 5 here. 1, 2, 3, 4, and 5, right? 5 data blocks. Instead of like really letting them reach these data areas and corrupt the file system, what we do here is that we first accumulate them in this temporarily logging area. We're like literally, if you want to update this thing, you put the new data here and remember that this block was block, like let's say it was block number 55, and you have to write block 55, right, later on. Then you say, what about this, right? So it goes into the block 77. So instead of updating, overwriting this area, you also accumulate it in this journaling area and remember the number of the block, 77. Then maybe you're like, this one was 103, and you say, look, the next one, 103, and so on, right? And you say, look, if you magnify this logging area, it will literally have the following. It will actually contain the data blocks, like you have those 5, right? Let's imagine you have the data blocks. You will have the numbers, like you say, this has to go, the first element of this array has to go to the block 55 in the data area. No, not data, but on disk. The second one goes to 77. The third one goes to 103, and so on, right? And the total number of those blocks which have to be written is 5, right? So you first accumulate everything in this data area and in this kind of journal saying that, okay, that's my future update. And then you write this 5 to disk. The moment this 5 hits the disk, the transaction is committed. If you lose power after that, after reboot, you will take a look at this journaling area, will figure out that this number is not 0, which means that there were some pending writes and you will essentially recover the file system by essentially copying those. You say, look, by copying the journal, saying, okay, this has to be copied into area 55, into the block 55, and you just will be doing those writes. This 55, this goes to 77, this goes to 103, right? They agree with this? So it's kind of like, it has a flavor of this soft update idea, because this is the last write which you do, right? And if you don't lose the power, you install those writes, and then you update this journal saying, okay, I have 0 pending writes in my journal. So next time, if you lose power after that, you're done. So you're good and you don't have to recover anything. If you lose power before writing this 5, then you simply lose the writes, right? So, but it's okay. File system is, you lost the data in your, like, you typed some, lines in your Visual Studio, those lines will be lost, right? Even if you clicked save, but maybe saved only moved them to the buffer cache, they didn't hit the disk yet, right? So, but that's okay. At least you can reopen the file and look at a slightly older version of a file, right? Which might look a little bit inconsistent for you, because maybe you started typing main function and it crashed halfway, so you have M and A, but nothing else, right? But as a human, you can recover. And we know you can recover, like, do multiple copies of whatever at the level of your text editor as well, right? But at least your file system is always consistent. You can reopen it after a crash, and you can easily, like, essentially access any file, and it will always be in a good, maybe not the most recent according to your definition of recent, but at least in a good state. Questions? So this idea is called journaling. And so this is actually implemented in almost all modern file systems, just because it's so much easier to implement it. Like the file system which you're running on your laptops will be using this journaling idea. So the journals will be more mechanically more advanced, but nevertheless, they are kind of similar. Question?
When the 5 is right at the first place, it means the whole stuff finished, right?
Yeah.
And then at this time, we should remove all of this.
Yeah, at this, like, the high level observation here is that you're writing the block twice. So first you're writing it in a logging area, and if you don't lose power, you're writing it in the area on disk one more time, right? Which means that you're paying twice the time for writing a block, right? So you're paying, like, you pay power, you're wasting power, but most likely you are also, like, if you have a write throughput of 100, let's say, megabytes per second on a typical spinning disk, then you only be able to write 50 megabytes per second, just because you're writing everything twice, right? So which is not ideal, but in a typical workload, writes can be asynchronous, meaning that you don't really care that they finish instantly. So only when you copy large amounts of data, this journaling idea will be in your way, because you really cannot catch up. But typically you say, look, I wrote something, but the write can hit the disk a little bit later. That's fine. You hardly notice, right? Question?
I mean, each time we finish kind of like you said, the transaction. When a transaction is finished, that means the file is there, right? So when it's finished, should we clear it, or?
Yeah, we cleared by writing 0 again.
Oh.
Right.
So my point is, how about we partially finish, like we finish 55, and
Yeah.
we do not even start the last one. What happens?
Yeah, you reboot and you start over. So you will again overwrite 55, because you still have this, you have the entire journal pending for you, 5 entries. You didn't clear them. You will do it again. You will write 55 again, but
if I also lost the record of like 77 and 106.
wait, hold on. How can you lose them? Because those hit the disk. So this sits on disk. The journaling area is on disk. So, and 5 is on disk, 55 is on disk, everything is on disk. And 5 hits the disk the last, meaning that you first collect the journal and then say, I have 5 entries in the journal.
So the journal is, I mean, it happens, you get 55, 77, but you do not get 103, right?
What do you mean you don't get it? Oh, so that, like, if you just like, imagine you're doing this file write, which I was trying to explain, and it involves 5 writes, and you accumulated 3 of them in a journal, but not the last 2 and crushed, then you lose the entire write. It will never hit the disk. So which means that if you say, okay, did I send my Falcon rocket to the moon and I want to make a record of it, you reboot and it says, no, you didn't, but the launch happened.
There's no partial recovery.
Right, there is no, and this specific. So there is like output consistency problem is there. So you may end up doing something twice just because you didn't have a record that you done something, like you launched a missile.
This is a question I've had for a while. Do computer components like memory and disk, are they able to retain some power?
Yeah.
So that even when the system uses power, they have a little extra boost to.
Correct. Yeah. So people started playing with those ideas, and I know that like disks, and specifically the disks which were used in file system arrays, like there is a business of selling you like large file system, right? So one big company is called NetApp, for example. So you buy a box, and we in the School of Computing used to have those boxes. I don't know if they have them anymore. And they say, look, we never fail because we tested everything, and we are so reliable and so fast. And to make it fast, they sometimes try to rely on the fact that the writes in flight will finish, so they have like an extra power capacity. It's an interesting game to play. And so like most recent Intel non-volatile memory architecture, when we're not talking about the disk, but talking about non-volatile memory, which has similar problems, also have like a power to essentially finish the writes, but there are some issues with that as well.
So does the log like contain multiple of these structures so that you can have like concurrent, right? Like they're kind of like.
Yeah, eventually it becomes a bottleneck, and it's up to you how to design it, right? So how ideally you would like to have multiple concurrent transactions, right, from multiple processes to be in a flight. And in x86 they have a number. It's limited by the size of this log, and so in x86 the number is small. In real journal you will have like a more advanced infrastructure to really like have multiple pending transactions, and they will be committed and cleared concurrently as well, right? Because some of them will be longer, but you want to avoid everyone waiting on this long transactions and stuff like that. So there is a design space for that as well. Any other questions?
If you like for devices with these on them, like, you can probably make some guarantees about like, being able to write.
Right, but there are some other semantic guarantees. So what if you really, like, it's a good question. So imagine you have a disk which has power, so, and it will complete all the writes, but what if you have like a real software bug in a file system, like which panics, for example, and then still the writes don't hit the disk because everything's stalled, right? So you have this problem of trading, performance for this rare chance of a bug in a file system. And it's, again, depending on the application domain, this trade-off can go one way or another. However, if you say, look, but what if I have this just file system, which is like super complicated, shared across like multiple tens of thousands of users, then like the chance of this software bug crushing one file and the entire data set is bigger. So you have to think of how to recover from this. It's not just the power. So then the battery cannot solve everything, unfortunately. And so it's the same, yeah. So that's essentially the high level line here. So you have to be, it's still an active area of research, how to design reliable file systems and stuff like that. Okay, good. So can we move on? So we're good with journaling. So this is the main, and this is how x86 implements it. So in all the file systems, do this as well. So because that's essentially the way to implement this consistency. Okay, so next layer, I wanted to come back to the inode layer, right? So because, and again, we already talked about it, right? So at a high level, this is the data structure on disk. So inside this array, there will be an entry, right? So it will just literally, it's an array of entries in x86, and this entry is there. So it's inode on disk, so disk inode, so which has this kind of like a type, which says whether I'm a file or a directory. It has the 12 direct pointers to say like the first 12 data blocks will be immediately referenced from the inode itself. Then there will be a pointer to an indirect block, and this one sits in the data area. And again, it has 128 entries, which allows you to essentially get a max capacity of a file, which is like 12 plus 128 multiplied by 512, right? So that's the equation, right? So it's not a big file, only 71 kilobyte in x86. But if you add another layer of indirection, so if you turn those guys into indirect blocks, then the file size is growing rapidly. So that's not a big problem here. Okay, so do we understand how it works? So since we already discussed it, okay. So like literally when you read a file, and as I was saying, so this kind of resembles a funky page table, right? Instead of in a page table, everything is immediately an indirect block, like a root of the page table. Here they make an optimization, and you can feasibly like think of a similar optimization like for an address space as well. It probably doesn't make sense because here it optimizes the typical use cases. We start writing the files from the beginning and then grow them. In an address space, you often start from the middle because there is an operating system kernel sits there and the libraries are loaded all over the place. So this is not typically used, right? So, but otherwise a similar kind of idea, right? So it resolves a logical address, which is like a virtual address with an offset within a file, into a physical address on disk. So it can be somewhere here, right? So, but conceptually, same thing, same kind of architecture. So radix tree, at least in this x86 implementation. Any questions about inodes? So I wanted to say that obviously x86, similar to a buffer cache, will maintain a cache of those inodes. So essentially, a frequently used inodes will be cached in memory and kept there, and there will be a lock-in discipline which says, okay, yeah, you're modifying this inode, you're adding entries, and then those inodes will be flashed back to disk as part of this transaction, right? So typically the file system, like all this file read and write operations, they don't directly use the block read and block write. They have wrappers, which instead of sending block directly to disk, send them to journal, right? So first to journal, then the journal commits, and the journaling subsystem, that's why it sits at the below the file system level, will promote, or like above the buffer cache, but under the files, will promote those writes to the journal and then to the data area later, right? Okay, we have the inodes question.
Are all inodes the same? Could because directly inodes wouldn't need as many addresses.
So in the directory?
Directly inodes.
Let me explain. No, in x86, all the inodes are the same. Although you can imagine a file system in which you optimize for a specific case and say that inodes can have different layouts. Like you say, we discussed before, you can have a type large file or small file. And then you can have a discipline for how to promote from a small to large, but maybe a small file will never have something like this, or maybe we'll have like an extra entry, like entry 13, just to like optimize a little, right? But you can, but not in x86, but you can think of it. So, okay, so cool. So when we reading or writing an inode, so we really, like when we execute this sysread system call, right? So remember, we execute a function which is called file read, and it gets this pointer to the file data structure, right? And just wanted to make sure that we understand where it comes from. So when the user passes us a file descriptor as an argument, right? So this file descriptor, remember when we fetch the system call arguments, we are very careful. So we test everything. We're like making sure that the user is not trying to crush the kernel, but really at some point, the file descriptor is an index into the file descriptor array. And this file descriptor array for each process contains the pointer to the file, right? So this is the architecture. So really when you do read of a file descriptor 3, it goes into the array, fetches the like file descriptor table, fetches an entry 3, and that will not immediately point to an inode, but will point to a file. Why is that? Because these two files might be pointing to the same inode, like in two different processes. Maybe you're reading, I don't know what you're reading, but like same file. And maybe you're reading position 55, like offset 55, and this guy is reading 120, right? So logically, each of them contains their own, like has their own view of what is that they're reading, right? That's why there is another layer of indirection, right? And also, like, as effectively, like just coming back to this file descriptor table. So it has a pointer to a file data structure. File data structure is conceptually simple. So it can either pretend to be a file or pretend to be a pipe. That's why, again, we say, okay, we're reading from file descriptor 3, but maybe it's not a file, maybe it's a pipe. And then like a file will have a type field. It says, okay, instead of reading from a file, just let's read from a pipe, right? So it just like implementing this polymorphism, hiding the multiple implementations behind one interface. So is that clear, right? So the block allocator, we discussed it, it's conceptually simple. So it's literally a bitmap. Getting the code correct is a little tough. So like I used to explain it in details, but imagine that you read in the units of 512, then typically your machine allows you to address like individual bytes, right? But you're really looking for bits. So there's a lot of bit scanning and like just make sure that you get the mathematics correctly to make sure that you convert bits to actual numbers and keep track of everything. But conceptually, it's very, very simple. So it's a very simple allocator and gets as dumb as you can imagine. Like just getting it right is a little hard. And the next layer above is a directory layer. So the question is like, what is a directory really? So what do you think it is? So when you type ls, like in your home, and home is your directory, and you have a bunch of files, like, I don't know, txt, something, whatever. What is it? Main.c, foobar.c. So how do you represent directories on disk? Do you have an idea?
So inode points to kind of a specially formatted file, which points to other inodes.
Correct. Right. Exactly. That's how it's done. So the directory is simply an array. So it's a file which contains those entries, which are very, very simple. It has a name of a file, let's say foo, and it has an inode number, like 55, which allows you to say, look, inside my directory, there are like foobar multiple files, right? So it's just a file of a special format, which is maintained by the file system, right? And you can imagine, so if you say, look, if you have a pass, something like user bin ls, right? So imagine like this is root and I have user here and it says 5066, then your algorithm, which takes this string, and if this represents a root directory, it scans each entries. In x86, it's very naive, but you can optimize saying, okay, I have an index to make sure that instead of scanning linearly this array, I can like have a better way of looking up the names, right? But eventually you reach user, you say it's inode number 66. So you go ahead, open 66. 66 internally will contain an entry for bin. Let's say it's 103, right? And then you essentially go to 103, open inode 103, which represents bin, and bin will contain an entry for ls. And you open this inode number 5, and this is your ls, right? So that's how you essentially traverse those names. And this layer, which resolves names or pass into inodes, is implemented with this function. We've seen it before. It's name to inode, name I, right? Remember when we were doing exec, we said, okay, well, you pass a pass to a program, and you get an inode back, right? And so here I have, I think I have an example here. So for example, when you do an open system call, again, you fetch the pass from the user. It's a string. You the implementation of the sysopen, the open system call says, okay, I'm gonna use namei function. Internally, namei will do this recursive traversal of the pass and return you an inode. And what you do here, you allocate a file, putting it into your file descriptor table. Remember that you allocate the lowest available file descriptor, and then you essentially like associate a file with an inode here.
IP.
Inode pointer.
Yeah.
IP? It's a local variable, sorry.
Oh,
It's just a local which you assigned here and you're done with it. After that, you return a file descriptor. Again, you're welcome to read the source code of x56, so it's not hard. So, but that's essentially, you got the idea. So directories are just special files which contain this arrays of names and inodes, right? So you can look them up and you can imagine how you write this code. So it's like essentially just scanning the stuff. So we already talked about file descriptors. So I think I'm actually done at this point. So any questions about file systems?
Does FD also inside inode?
FD?
Yeah.
No. What is FD? This one? No, FD, we just talked about it. Let me show you again. Where's my picture? Hold on. This, for example, this one. Oh, this is a pipe. Okay, let's not use a pipe. So this is, so imagine you, instead of doing a read, you do open, right? Open internally, like when you implement open, it will take a pass like user bin ls or something, right?
Yeah.
It will look up the pass by traversing the directories in a file system. It will eventually figure out an inode which corresponds to ls, right? And this IP will be like the pointer to this inode will be assigned to a file entry, which will be assigned to your file descriptor table. So it will, in this specific example, this file descriptor is number 3. That's an integer which user sees and can come back and say, okay, read from 3. But really the pointer is from a file descriptor table to a file data structure, FD. And then internally it will contain inode, a pointer to an inode in memory.
There is a table to maintain the pointer. There's a table to maintain the inode.
No, it's I don't have a source code for it. It's not a table, it's just a data structure. So this is your file descriptor table with some number of entries. Each of the entry contains a pointer to a file. A file contains a pointer to an inode. Question. What's the question or not? All good. Okay, so done with the file system and largely like we actually covered the entire book of x56 at this point. So we kind of understand how everything works, supposedly. We'll come back on Tuesday and I will draw you one more picture, which is a map of how everything evolves from boot to running a process, context switch, stuff like that. So kind of to make sure that you have it in your head, and then we'll solve some previous exams, I guess, and then good luck with the final. Okay, don't forget to finish the homework. We moved it from Tuesday to Wednesday, so I will have my office hours on Tuesday. I'll try to help as much as I can. Okay, see you guys.